Let's review some of the previous stuff. So we discussed the chain rule of the probability last week. So chain rule of probability is, first of all, this is general product rule. So where given a joint probability, so you have multiple variables and you want to consider the joint space of those multiple variables. So all of these n different variables, they are all moving separately. Maybe they are independent, or some of them may be dependent. Well, we don't know the relationship between the variable, but still we want to somehow describe the space that those n different variables are creating. So we can do that in terms of the probability, but at the same time, since we have n different variable, it's basically exponential space in terms of the computation. So where people came up with a way to decompose this big joint space. So if you use this chain rule, you can equivalently handle the same variable space in terms of probability of one variable multiplied by probability of another variable given the previous one. And the next one, yet another variable and all the previous one multiplied by next variable, all the previous one, and so on. So eventually you have this. So at the end of the day, you will have n different probability term. And the advantages of doing this, so like I mentioned, this one, left-hand side, this space is joint space. You can omit this description. So joint space is basically exponentially large. So in terms of the number of variables, where you are growing the search space of your probability space. But if you decompose things in terms of multiple probability term over here, so right-hand side is easier to handle. And although we have a long expansion of n different variable, the basic principle that I applied on the first expansion is given here. So let's give a moment, and I will remove my writings. Okay. So the expansion was sort of long, but the key principle is given here. So if you have a joint space of two different variables, you can pick any of them and write the probability and condition them for the next one. And this is again equivalent to this probability. So depending on the order you choose, the conditioning part is changing. But as long as you will maintain the principle right, you can expand the original joint space no matter what. And you can give some description of this expansion. So left-hand side, first of all, this is the joint space of these two variables, where it can be described in terms of one of the variable multiplied by the conditional probability. So this kind of decomposition has been used in many applications, especially involving some temporal stuff or sequential data. So last time we discussed one of the example from language processing. So if I have a sentence like this, well, there are multiple different approaches to model this in terms of probability, but one of the common technique is described in the slide. So what this sort of expansion is describing is where you have different words. So each of those W representing individual word. So probability of I, probability of go given I, probability of 2 given go and I, and so on, by writing some kind of a probabilistic notion like this, where you can model, where probabilistically model this sentence. So existence of this sentence can be expressed in terms of probability. So, well, you don't need to understand the concept completely, but we'll just get the sense of it. So we are sort of chopping a long sequence of data and try to express this long sequence of data in terms of probability. And using this chain rule, we can make the computation of those probability easier. So that's a sort of big idea. And the big idea is sort of formalized using Bayes rule. So we are going to discuss that today. And also Bayes rule is we're sort of connecting to one of the main tasks in machine learning, that is inference. So if you look up the dictionary, where probably this one, so one of the description in the middle, that is the meaning that we seek. So in machine learning, when you say inference, well, that is exactly the act of passing from statistical sample data to generalize the population parameter. Well, using the population parameter, eventually the goal is to calculate the degree of certainty or degree of uncertainty. So we use sample data to model or express. We use sample data to model or express the degree of uncertainty. So this is what we are trying to do. So we are going to talk about two things. One is Bayes rule, the other is inference. And first of all, the term Bayesian is used to refer inference methods that represent degree of certainty using probabilistic theory. So it's quite general. So nothing special yet. The important tool here, though, we are going to leverage Bayes rule. So we are going to use Bayes rule to update the degree of certainty that we are modeling. So let's get into it. So Bayes rule. More concretely, it can be described in this form. So from now on, we are interested in modeling some probability, where here H is what we want to model or what we want to predict. And Y in this notation, representing observation. So we want to model a conditional probability that is interested in our modeling target given some observation. And this can be expanded in this way. So the left-hand side becomes the right-hand side. But the idea here, so this formula, this is actually what we have been discussing already. So let's bring this to a clean sheet. So let's try to think about this formula in this way. So initially you have this term, joint probability. This is equivalent to this, right? So we expanded it in terms of the chain rule. And this is again equivalent to P Y. So even though you change the order of expansion, it's okay, like we discussed it. So you can expand the original joint distribution in terms of one probability, conditional probability, and you can switch the order. Now let's forget about it and simply bring this to the other side. So I'm going to divide both sides in terms of Py equal Y. So it's going to be removed. And I'm going to divide it by Py Y. And we made Bayes rule. So Bayes' rule is nothing but a description of the chain rule of the probability. And it has some meaning. So behind of this expression, this term over here is commonly referred to as prior distribution. So this is representing my base knowledge. So before I saw any sample data, before I see any sample data, PH over here is representing my prior belief. And I have seen some data. So the term in the middle, this guy is representing probabilistic notion of my observation. And eventually you will get to what you have on the right-hand side. That has a name, posterior distribution. Posterior distribution representing our updated belief after we see the data. So this is a posterior belief. So Bayes' rule is basically describing your original belief is changing after you see some set of data. Here you have one additional term py. This is often called as marginalization term or partition function. But this guy does not really affect the result in terms of decision making. What it is posterior, regardless of the marginalizations. Posterior is basically proportional to likelihood multiplied by the prior. So let me remove the handwriting after giving a 5-second pause. And basically we are interested in this guy, posterior, and likelihood, and prior, because this guy does not affect my decision making. The thing is, where I'm interested in the posterior, and posterior is only proportional to. So this is red proportional to the product of my likelihood on the sample data and my prior belief. So basically what Bayes' rule is defining is where my belief changes after I see some set of data. Well, here are some additional formula, but we'll get to it later. So we can express Bayes' rule, basically represent the transformation process of our belief state. So we have some state in our mind, and it has some kind of tendency, and we want to express it in terms of the probability. After we expose it to some new observation, maybe our belief changes. So we want to model that in terms of the probability that is Bayes' rule. And Bayesian inference is using Bayes' rule to update this entire thing. So here are given observation where this is your prior knowledge and what will be your posterior knowledge or posterior belief. So that is what Bayesian inference is basically interested in. All right, let's move on to the multi-hole problem. And this is actually describing a game. So there is a game show, and in the game show, you're invited as a game player, sort of. And you are playing with 3 doors. So door number 1, for example, door number 2, door number 3. And the rule is you first have to select one of those 3 doors. So out of 3, you pick one, but you don't open it. And after you pick one door, the game host actually opens one of the other 2 doors. So if you pick the first door, the game host will open one of these 2 doors. So obviously, the game host know where the price is. So the door with non-price item that is going to be opened. But anyhow, so you first pick a door and don't open, and then game host will open the door that you haven't picked. And after that, still you have two unopened door. So you have a second chance. So you can change your choice, or you can stick to your original choice. So at the end of the day, you have only one choice of door, and whatever behind of the door, you will get it. So the idea is only one of the door has the price, for example, car. So this is a Monty Hall game, Monty Hall problem. So where you are playing this game, and now suppose where you have initially chose door number 1, and where game host actually knew where the price is, where based on that information, game host opened door number 3. And now it's your turn. So you have choice of sticking to door number 1 or switch to door number 2. Or maybe you can make an assertion that changing or sticking to one of the door actually does not making any difference in terms of probability. So we want to see which of these statements are correct using Bayes' rule. Well, intuitively, maybe you would like to choose statement number C, but well, let's see. So here I enumerated all the possible cases. So your initial choice was door number 1. So maybe behind of that door, the price was there. So if that's the case, if you stay, you will win. And there could be a case that the price was actually behind of door number 2. In this case, if you stay, you will lose. If you switch it, you will win. And there is a third case that is actually not possible because the game host opened the third door already. But if the car were behind of door number 3, then you have to switch to door number 3 to win. So given this information, let's try to compute the probability of which door the game host opens. So if the car was behind of door number 1, I initially picked the right choice. And the remaining 2 doors where there are no price. So for game host, where there is no meaning of choosing one of the doors. So basically you have half and half probability. The game host can open either door. If the price was behind of door number 2, where the game host will never open door number 2. Instead, the game host will open the door number 3. If the car was behind the door number 3, the game host will never open door number 3 and he would open door number 2. So these are sort of additional information we can formulate. So clearly, although I didn't describe Y is the door number the game host opens, and H is the actual location of the price. And given that, let's try to calculate the posterior probability after we have seen which door opened by the game host. So we want to model the posterior probability where the price is. And this is the observation. So the game host opened door number 3, and this is my target. And this conditional probability can be expanded as the right-hand side. So probability of game host opens door number 3 while the location of the price. So given this, next thing we want to do is simply assigning each of those values. So we can consider 3 different cases where actually there's a door, where actually there's a price at behind the door number 1, behind the door number 2, behind the door number 3. So where price was behind of door number 1, given the game host opens door number 3, you can calculate the probability as like this. And the price location is door number 2 indeed was calculated in this way. So the prior is basically uniform. The price can be anywhere out of those 3 doors. So it's always 1/3. So you have that over here. Only the difference is the likelihood from the observation. So the probability of game host open door number 3, this is what happened. This is my observation. Given some condition, depending on the location of actual location of the price, the likelihood changes. So the first case, it's half. The second case, it's 1. Third case, it's 0. So this is something we have calculated in the previous slide. So at the end of the day, if you calculate the ratio between these 3 conditional probability, these 3 proportional to 1/3, 2/3, and 0. So you initially picked door number 1 and host showed door number 3. Then probabilistically, it's better to switch your choice. So basically, the Bayesian analysis is telling us, well, pick one door, and after you look at the door that game host open, well, change your decision. This might be different from the first impression that you got, but well, if you try to exclude all the emotional thing and try to analyze the situation based on what you have studied, well, this is the analytical result. So this is quite counterintuitive, but this is the reality. And the trend is actually visible from the experiment. So you can simulate the scenario that we described. And if you repeat the simulation 50 times, well, this is the number of wins after you switch your initial choice. And this is the number of wins where if you stick to your initial choice. So basically, it's double. And if you repeat this 1,000 times, the tendency becomes more clear. So it looks exactly double, and that is what our analysis is telling us. So probability 1/3, 2/3. So basically, switching gives me twice the higher chance of winning. So this Bayes rule is giving us a framework of something we call as learning. So we have given observation, and based on the observation, we want to update our confidence model. And confidence consists of prior and posterior. So prior is my former knowledge before I see any observation. And posterior is updated knowledge or updated belief after I see some set of data. And the set of data that I observe is represented in terms of likelihood. So Bayes' theorem is more formalizing the Bayes rule in the framework of learning. So basically, it's describing the same formula, but the analysis sort of became more general. So zeta is representing my parameter or my model. So the prior knowledge about my model, so probability of my model is true before I see any data. And full purpose of doing this is getting this guy, posterior distribution. This is the probability of my model is correct after I see set of data. And this is the likelihood. So it can be understood as the evidence about my model. And that is represented in terms of likelihood. Likelihood can be understood in a sense where this is unnormalized probabilistic quantity. Still, we have one more member that is probability of data. So this is the total probability of data taking into account all possible hypotheses. But well, like we discussed, the data is not changing. So well, we normally don't consider this. Instead, we simply model the posterior in terms of the ratio. So we seek the proportional to relationship between the posterior and likelihood multiplied by prior. But still, we want to be clear with the definition of this guy. So this is again total probability of data when you take into account all possible hypotheses. All possible hypotheses means all possible model. So if you marginalize your numerator over all possible model, then this is what you get. So this is well, by definition thing. So we discussed the key concept of Bayesian approach and Bayes rule, Bayes theorem, things like that. Actually, there is two big schools of statistician. So one is Bayesian, the other is pre-quantist. So Bayesian is well, sort of more traditional in terms of history. So this has been well, the traditional concept of statistics. And well, somewhere in between 1900, where there was a big emergence among the pre-quantist statisticians. So pre-quantist, key interests of pre-quantist statistics, where pre-quantist treats probability as a measure of frequency. So we're considering a coin with some fixed probability, where we are not considering a one case of coin tossing. Instead, where we want to observe multiple different cases, and each of those trial has a correct answer. This is a sort of assumption that pre-quantists have. So pre-quantists use probability of hedge in terms of analyzing the observation or summarizing the observation. On the other hand, Bayesian tries to use probability as a tool to abstract some concept and try to represent the belief or represent the uncertainty towards some trial. So here, big assumption is each trial has uncertainty. And try to model the probability as an expression of confidence. Well, suppose that I have a coin and I tossed it and I got it on my farm and I haven't opened my farm yet. So I don't know whether it is head or tail. Given that, Bayesian thinks that well, there is a probability that I see head, 50% of chance. So that's what Bayesians think. Well, pre-quantist says things in different ways. So there is a correct answer. I simply don't know about that. So there is no such thing like 50% of chance. So there is an answer, and it could be only 100% or 0%, but I simply don't know that. So well, given this observation, well, pre-quantists, well, they observe 1,000 different cases, 100,000 different cases, and try to use statistics to summarize the event, to summarize the observation. Bayesians tries to observe those trials or experiments and try to model the uncertainty towards each single trial. So these two are sort of different approach and different perspective towards the probability. And here comes some additional comparison. So sort of one-to-one comparison. And well, I don't really like this comparison much, but well, there are some stuff like that and maybe some to think. So I kept this on this slide. But well, take a look. Even if you don't understand each sentence completely, it's still okay. Important part is what these preconceived and Bayesian approach mean to us. Where in machine learning, we are using both approach. So we're sort of using mixture of techniques, place to places. So for example, when we try to model, it is basically using preconceived approach. So we seek for a certain value for our model parameter or something like that. But the entire framework was actually developed in terms of preconceived point of view. And there could be some cases where you have multiple different models. And out of these multiple different models, you want to pick the best one. Well, if you want to do so, then Bayesian approach is the answer, things like that. So throughout the study of machine learning, you will use the both schools outcomes, both schools residue in your experiment and in your study. So both of the approaches are meaningful, that's the idea. And today we try to expose ourselves to Bayesian theorem and Bayesian rule.